Hi there, seniors. Just thought I'd record this quick video for you guys so that you have maybe a clear understanding. And I don't know why you don't have a clear understanding because I looked at the assignment. I'm like, wow, there's no problem with this, except that I had to edit a few things and whatnot. So thank a couple of your colleagues for bringing up your issues to me. So if we go into the assessing ET assignment, um, and you're looking at this, and I really love this mist over the mushrooms image, but Tuesday we're going to look at some of your data from the ET gauges. You're going to keep collecting data from those, by the way. You're going to keep collecting that data because Mrs. Cluse is going to make good use of it. All right. So anyway, we'll talk about your data a little bit, and then we'll also talk about what you've done with Model My Watershed, which is all these things here. The things I want you to really focus on here are not so much the ET specifically, but looking at the holistic view of a watershed in terms of the bathtub, right? So you've got precipitation coming in and you've got these other variables going out, and they should balance over the course of time, over the course of some period of time. They should balance. So if we create a model or model a watershed, we should find that that's the case. We're going to do two things. You're going to do two things. You're going to create a site storm model, and you're also going to create a watershed multiple year model for some watershed. I don't really care what it is, but you're going to click on this link up here. This takes you to Model My Watershed, and it tells you here to use continental U.S. medium resolution. That's important. So if I go there, it automatically wants to pull me out of Mount Jackson. Let's say I wanted to go some other place. I don't know. Let's go to my hometown. Why not? Maple Heights, Ohio. And because that's what I thought would be kind of cool. All right, so I'm going to go to Theodore. I grew up right around here on Theodore Street. I want to delineate a watershed. I want to identify my home watershed. I'm going to choose continental U.S. medium resolution, and then I get this cool little cursor thingy, and I'm going to click on the map, and then you'll see it working over here, thinking, looking at the topography and the nearby streams and all that jazz, and eventually it's going to delineate a watershed. Eventually, wait for it. Waiting. It may take a bit of time. Or a lot of time. Have a cup of coffee nearby. Maybe this is where you go check the news or read up on some really cool, I don't know, piece of geo news out there. It normally doesn't take this long, but be patient. Well, while that's working, because I don't want this video to last 10 minutes, here's a watershed that we created here briefly. This is over in Page County. So I just clicked on a place and it identified the watershed for that area. And if you do that, you'll get this where it's analyzing the watershed, but up here at the top, you'll have analyze, monitor, and model. We're not interested in these first two. We're interested for this assignment. We're interested in modeling it. And there's two options: a site storm model, which is a one storm model. If I click on that, it's going to calculate the results. But what I'm going to have to do is adjust precipitation, because I said a 2-inch rainstorm. So let's say we adjust this to 2 inches, which is about 5 centimeters, right? Let's just go with that. And eventually calculate the results. Did this watershed ever finish? Still delineating there. It'll calculate the results. Actually starting to wonder if my Wi-Fi is working. Yep, it is, apparently. Anyway, it'll calculate some results eventually. I'm going to pause the video. Okay, hey, we're back. And this is now the watershed of my home place, right? It's still analyzing. You've got the 3 tabs up here. Again, I'm interested in modeling this watershed. And I'm going to look at the site storm model. I'm going to go ahead and let it calculate results. I'm going to pause the video again and come back here in a moment. All right, I've got my results. So this is for a 2.5 centimeter rainstorm. That's about 1 inch. What I said in the assignment was to make it 2 inches. So we're going to up it to about 5 or so. And we'll see that this will automatically adjust. So when I add more rain, or less rain, you'll see what happens to the variables here. Runoff, evapotranspiration, and infiltration will adjust. And you can imagine as I add more rain, there's going to be probably less infiltration. Is typically what happens, and more runoff. And that's because, of course, the soil by that point is super saturated and can't take any more water. And that's what you would expect. And evapotranspiration diminishes as well. At some point with large rainstorms, individual storms, runoff dominates because that's just what happens, which is why you have places like Puerto Rico, like right now where there's so much flooding. Pakistan is a mess. One third of the country was flooded because they had so much rain. It just had nowhere to go but run off and then pool around and so forth. So anyway, that's the site storm model. So you can download the data as well. If you download this, it downloads as a CSV file. You open that. All it's going to give you, it's not a very exciting file. It's just basically that, and you can get rid of those numbers by making that bigger. But it's just showing you the volume of water for one. Well, this was a 20.75 centimeters rainstorm, so a pretty big rainstorm. But it does give you those values. So if you know that, for instance, you're getting a rainstorm of 20.75 centimeters, and you know how big the watershed is, you can multiply those numbers and get a volume. You can make sure the volume is in cubic meters, so convert things, and then you can begin to look at water balance here a little bit for a particular storm. So if I were to go back and look at this under the original 3 tabs you had up here, there it tells you what the areal extent of the watershed is, and it gives it to you probably in square kilometers rather. And then all you'd have to do is basically convert that to meters. You take your precipitation, convert that to meters, multiply those two together, and that gives you the volume of water from precipitation. And then you got the volume of water from runoff here, ET, and infiltration. And you can set those equal to each other and see if they balance out. That's for a single storm. But that's an interesting way of looking at it for the water balance for a particular storm. But there's another way to do it, which is to look at it over time, which is more of a climate question. So that's a weather question. This is more of a climate question. We want to look at the multi-year model, which is a 28-year model that Model My Watershed uses. I'm going to pause it again. Okay, we're back. So I have a drop-down menu. We're not interested in water quality. We're just interested in hydrology. And I can look at the different variables that, some of these are the only inflow is precipitation. Everything else is pretty much an outflow, or a bathtub is like, the faucet is precipitation. Everything else is the drain. So in an ideal situation, in a 28-year course of time, you would have balance on both sides. You should end up with a 0. Precipitation equals everything else should be 0 if all things are working the way you expect them to. Of course, this is a model, and models are always wrong, but can be useful. So here's your numbers. You can look at the graphs, have fun with that. You can see during certain times of the year, ET is more dominant over the course of time. Again, these are average. These are climate averages. If I scroll down to the bottom and download this data and open that up, this data is a lot more interesting, and I get a spreadsheet. Now, if I want to calculate water balance, I'm going to go ahead and make this wrap text so I can see my variables here. I know precipitation's got to equal pretty much everything else, so I can pretty much do this. I can say equals precip minus, and then just make everything else a part of a quantity here. Right? And then I can close the parentheses. And it looks like for the month of January, over the course of 28 years, we are typically in a deficit of precipitation and so forth. But if I drag all those down, it looks like I'm in a deficit entirely. And that's where that's where the question about this being a model comes in. This number should probably be 0. So what's going on there, right? I could sum these numbers as well, by the way, and say what my average, actually it's got totals down here. So you've got 93 inches of rain, or 93 centimeters of rain per year. Divide that by 2.5 to get inches. Anyway, point source flow. We're not really interested in that. We can actually get rid of that because that's actually not a critical thing for what we're doing, and we'd have to adjust my equation accordingly here. And then that didn't change anything because those numbers are all zero anyway. So another one that's curious is subsurface flow, and that's groundwater flow. Is that critical? What happens if I get rid of subsurface flow? Because that's not no one that we're necessarily measuring directly. So let's go ahead and get rid of that for the moment. And you can see that kind of balances January out a bit. If I do that with all of them, I get a little closer to zero. But you got to remember, if you're going to adjust the model, you're going to need to be able to talk about why you're making those adjustments. At this point, surface runoff, stream flow, I've taken D out of the equation, and I have ET, should all equal precipitation for sure. This would be what this number would actually be is your change in storage. I haven't mentioned that variable. So this would mean that over the course of 28 years, we're losing water from the ground and any reservoirs on the surface. And it may be that over the course of 28 years, we are losing in that Maple Heights, Ohio area, 15 centimeters per year out of storage, or cubic centimeters per year out of storage. Here, the variables, by the way, are measured just in a linear centimeter. You can do this. You just have to take the watershed area out of each of the variables. As long as you're comparing similar units to similar units, you're all good here, okay? Cubic volumes are fine. An individual, if you want to take the area out of all those variables and just use a water, basically would essentially be a water depth person, you can do that. You can still compare it with the water balance equation just fine. Units all have to be consistent, but they can be the equation itself can be unit independent. The only thing that's consistent across all of these, and in this spreadsheet, and of course, again, in this spreadsheet, they're using cubic meters instead of straight centimeters, is the area of the watershed. Now, the area of the watershed, if you go back to the original watershed page, shows up over here. It's 18 square kilometers. Not a very big watershed in this case, but it shows up here. So what do I want from you guys? I want you to create these two models. I want you to play with the numbers a little bit, use the water balance equation, and then we'll come in, we'll talk about what you found out, and talk about, we'll spend a little bit of time with that on Tuesday. But I want you to turn this in before you come to school. And I'm looking for a couple of paragraphs, write it up as a sort of a lab report, just a couple paragraphs, starting off with like why you're doing this. You're looking at a watershed and water balance in a watershed for an individual storm and for on average. So you're looking at a weather event versus climate, essentially, and trying to understand what the change in storage looks like in that watershed in both situations. And then talk about what you find out. And that's it. Conclude it. You're done. Don't write more than a page. Put some images in there. That may extend it beyond a page. That's fine. But don't write more than a page, please. And double space it. And keep it simple. I want you to play with the model, have some fun with it, and be able to converse about it a little bit. Okay? So this is sort of preparation for Tuesday. All right? I'm going to stop this here and have fun.